So we have difference in chemical potential is given by the chemical potential on, say, the inside minus the outside. Okay, this is for a cell. And the cell we were particularly talking about were neurons. Okay? This is convention. I need you to use this convention. It'll become especially important when we're also introducing the electrical potential contributed by the different signs of the ions, because then if you flip it, all of your answers will always be wrong. Okay? However, something to maybe keep in mind is what you're going to find in your book if you're reading it is maybe just mu2 minus mu1. Okay, and so then the question goes, how do I decide which is 2 and which is 1? The way to always think about this, the way that helps me best, is always write it as final minus initial, right? Final state minus initial state. And in this case, that means that inside is my final state. But if I want to move things out as opposed to in, so by convention, what I'm saying is this difference in chemical potential is for I am outside and I move in. This is initial, this is final. So if I go the other way, then you can either switch these or flip the sign, okay? The sign will just change. And so this was one where on the homework, which direction sodium was moving and which direction potassium was moving, one of them you needed to flip the sign to get it correct. Okay, and so I just recommend, sort of asking yourself, I'm cool if you always want to write it as, final minus initial, and then ask yourself, which way am I going, okay? However, when we get to electrical potential, in minus out will be the resting potential, and so the resting potential won't change. It'll always be in minus out. So just sort of ask yourself, like, which direction things are moving. So we have that free energy is equal to the difference in chemical potential times the change on the inside in the number of moles or number of molecules. And so if this is less than 0, then we know that direction of movement is spontaneous. And so if this term here is positive, okay, if the chemical potential on the inside is greater than that on the outside, in order for this to be spontaneous, this term would have to be negative. Okay, so a way to think of this is that we will lose particles from the inside to the outside. And then alternatively, if this term here is negative, such that the chemical potential of the inside is less than the chemical potential of the outside, in order to be spontaneous, this term, this change in the number of moles or molecules on the inside would have to be positive. So things would have to be flowing in, okay? Molecules must flow in this case, in order to make dg be less than 0. And so direction of flow, direction of movement is from higher numbers of moles or molecules to lower. And these are some notes I actually provided. This set of notes is already available online. If you looked at the handwritten notes from last time, I put these there. Okay, I'll go through it quickly again. So something to pay attention to, and I just mentioned this, the difference between G versus DG versus delta G, okay? These are not all the same. If you're being asked for the difference, the change in free energy, delta G equal to the integral of the difference in chemical potential times the number of molecules moving. This is the number of moles or molecules moving between two states. This is a difference, again, between two states, meaning these could be solutions A and B, might be sort of the narrative of the problem. These could be the in and outside of a neuron. These could be across a semi-permeable membrane. You could say, oh, you have glucose solution in water and there's a membrane that the glucose can't get through, but the water molecules can move through it, some sort of storyline in that nature, how many things are going to move from the left side of the membrane to the right side or whatever it might be. Okay? So you have actually you're calculating a difference between two things actually moving. Whereas here, okay, remember we have DGI, DNI, this is going to be molecular chemical potential. If you see the word molecular, you know I want it in individual molecules or individual ions, whatever it might be. DGID, lowercase n sub I, this is my molar chemical potential. And I can always switch back and forth by dividing number of molecules by Avogadro's number. So if you rearrange this, and you get, rearrange this as I did on the board so that you have dg is equal to u sub I, dn sub I, and you integrate, okay, this is free energy is equal to the chemical potential of species I times the number of moles I have of species I. Okay? And if I have multiple species are reacting, then I can, maybe something like A plus 2B is forming C plus 2D, whatever it might be. Then when I actually want to calculate, say, G for the initial state, before the reaction starts happening, right? Nothing has happened, okay? DG is going to be given by the sum over all of the different types of molecules that are involved. And G for the initial state will be U sub A. Number of moles of A, you can sum these up. I have mu sub B times number of moles of B. And this is an example we'll look at in a second, later on today. If this was sort of the initial state, then when I want to calculate, say, calculate G for the final state, once all of the reaction has happened, okay? This is sort of maybe before reaction. And then G for after the reaction is going to be given by, can you see this? There isn't enough room here. Maybe if I pull it forward. So after the reaction, I'm going to have, I've used up all of A and B to make C and D. Okay. So now I have how many moles of product C do I have times the chemical potential of product C plus the chemical potential of product D times the number of moles of product D that I have. And so when I want to calculate delta G, this is equal to my final state minus my initial state.